So good afternoon and welcome back you all. So this session we are going to look into some of the basics of ANOVA. ANOVA is analysis of variance. So this ANOVA is a statistical tool which is mainly used to determine the variance that exists between two data sets. And also we are going to determine which selected input parameters have an higher influential effect on the output response. So this ANOVA is developed by Fisher, an English statistician who is also the father of design of experiments. So initially this statistical tool ANOVA was used for analyzing the agriculture data, and later on we started using this in all fields for data analysis. So even though it is widely spread and utilized and applied, many researchers and engineers failed to validate some key assumptions before applying this ANOVA to their data sets. So what are the assumptions that we are going to make before analyzing the data that we have? Is a very, very key in analysis. So this ANOVA is one among the most frequently employed statistical technique in both social and engineering sciences because it provides a more flexible methodology during testing the differences among the means of data sets. So we have a data. In that data, in between two variables, we are going to find out the variance. So that is where we are going to use this ANOVA. So this ANOVA, as told, it is a statistical technique that is applied to a data set. Okay. How we are going to develop these data sets? The data sets can be developed in two different manners. One is by means of experiments, or by means of non-experiments also we can develop the data sets. For example, by making a questionnaires. In management sciences, people make questionnaires, they collect data. So without experimentation, the management peoples will get the this questionnaire data, and they will analyze it for the variance, or by means of a feedback. So by both experimental and non-experimental, these data sets can be obtained. So during the analysis of data sets obtained using ANOVA, we have to be very, very specific about which factors or variables are assigned as dependent and independent variables. Because yesterday itself we have seen that the dependent variables are the outputs, whereas the independent variables are called as input factors. Depending upon the variation of inputs, the outputs varies. So the outputs are dependent on the value of inputs. That's why we are going to classify the outputs as dependent and the inputs are as independent variables. So before going for this ANOVA, we should formulate some hypothesis. Everyone knows about the hypothesis in statistical manner. Hypothesis is nothing but an assumption about a population. The population is nothing but a samples. So how many samples that we are going to obtain? So for example, I am going to compare the surface roughness of two different tools. The surface roughness of the machined surface machined using two different tools. For example, a HSS tool, that is high speed tool, or by using a carbide tool. So two tools I am going to use, and I am going to machine a workpiece, and the surface roughness is compared. So the mean surface roughness of X tool is less than or equal to the Y tool. So this variance we can study, or the mean tool life is more than or equal to 2 hours. The tool life is the time period for which the tool works perfectly. So these are the some of the hypotheses, that is the assumptions that we are going to make. So based on these assumptions, we are going to have two different types of hypotheses. One is null hypothesis and the other one is alternate hypothesis. The null hypothesis is the preferred assumption of an population, the sample populations. So the preferred assumption, what I am going to assume. The alternate hypothesis is the opposite of the null hypothesis. In the first example, that is mean surface roughness of X tool is less than or equal to that of Y tool. So that is my null hypothesis. But in the alternate hypothesis, the mean surface roughness using X tool is higher than or equal to Y tool. So it's just the alternate or the opposite to that of the null hypothesis. The example for null hypothesis and alternate hypothesis is the mean number of defects per assembly in the population is more than or equal to 2. So this is I am going to assume. I am going to make some assumptions in the selected population that the number of defects per assembly is more than or equal to 2. So this I am going to assume. But in the case of null hypothesis, the number of defects in the assembly is less than 2. Because in null hypothesis I have taken the number of defects is greater than or equal to 2. So opposite to that is it should be less than 2. So that we are going to take it in the alternate hypothesis. So this ANOVA is formulated based on this null hypothesis and alternate hypothesis. The null hypothesis is represented by means of H0 and the alternate hypothesis is represented by means of H1. Now we come across another term, that is significance level. The probability with which the null hypothesis is rejected due to an error. Because error exists in all the systems, so there may be a chance that due to some problems the null hypothesis may be rejected because of an error. Even though the H0 is true, the assumption what we have made is true, but due to some error we are going to reject that null hypothesis and we are going to accept the alternate hypothesis. And the probability with which we are going to reject that null hypothesis is known as significance level. Even though we have many approaches in order to eliminate the error, there may be some sampling errors, inferences in the sampling, which will account for some types of errors. Even a measurement error will be there, or this error may happen due to human So that is also possible. So there will be always a certain type of error. So that should also be taken care of. There are two different types of error that arises because of the significance level. That is the probability of rejecting a null hypothesis due to an error. The type 1 error is, it is the probability of rejecting the null hypothesis when it is true. I have made an assumption which is the null hypothesis, and alternate to the null hypothesis is the alternate hypothesis. So because of some error, even though my assumption is correct, I am going to reject that assumption, and that comprises the type 1 error. The second type of error is the assumption that I have made is wrong. So alternately, I have to accept the alternate hypothesis. The assumption that I have made is wrong, so accept the alternate hypothesis. But because of some errors, I am going to accept the null hypothesis instead of accepting the alternate hypothesis. So this comprises the type 2 error. So rejecting the null hypothesis when it is true is type 1 error. Accepting the null hypothesis when it is false is type 2 error. So what is the need for ANOVA? Because this is a statistical tool and we are going to use this in all means. What makes it the ANOVA to be applied? We have different types of sampling test, and among them the Z test and test are more common. The Z tests are commonly used when we have larger sample sizes, whereas this T test is used when the sample size is smaller than 30. So depending upon these sample sizes, we have to go with Z test or T test. But these Z or T tests will have some limitations. When comparing most of the two sample means. For comparing two sample means, this Z test and T test have some limitations. So, because of this only, we are going to move towards ANOVA. Hence, one can use or apply this analysis of variance when the number of sample is more than 1, because we need a variance. A variance exists only between two variables. The variance exists only between two variables. So when the number of samples is 2, then only we can use ANOVA, because a variance exists only between two samples. And also to check the effect of the factors and their interaction effects. The factor effect is factor A, factor B and factor C. Their interaction effects is AB, AC and BC. So these AB, AC, BC are the interaction effects. This ANOVA is formulated for the input parameters over the response variable. The response is nothing but the output. This ANOVA uses F test. This ANOVA uses F test, which will provide a meaningful inferences that relates to the effect of the response variable. So instead of Z test and T test, in ANOVA, we are going to use F test. F test is the Fisher test. In statistics, everybody knows the Fisher test. So we are going to use this Fisher test to identify or to provide or to interpret a meaningful inferences that relates to the effect of on the response variable. So the effect provided by the input variables on the response variable. The response variable may be a surface roughness, maybe a metal removal rate, maybe a flank pair. Likewise. So what is F distribution? So the F distribution is a probability density function. The F distribution is the probability density function. So it is the function of the ratio of two independent random variables. The two independent variables should have a chi-square distribution. The two random variables which are independent, the independent are nothing but the input variables. The independent variable should follow a chi-square distribution. That is very, very important. It's the ratio of two independent random variables which is divided by its number of degrees of freedom. So F test is a probability density function which is the ratio of two independent random variables, and that should have a chi-square distribution and divided by the number of degrees of freedom. So by using this F distribution, we are going to identify the model that best fits the population. In the morning also, we have come across the statistic tool in RSM, where we will be having the sequential sum of squares, then R square value, adjusted R square, then predicted R square, based on which we are being suggested to use linear or 2f1 or quadratic or cubic. So to identify the model that best fits the population from the data sampling, it will tell us. So what is meant by F value and P value? Because these two values we are going to use it in on our table. So the F value in ANOVA, that is the Fisher value in ANOVA, is used to answer the question: is the variance between the means of two populations are significantly different? So ANOVA is to determine the variance between two input parameters over a output. For example, cutting speed and feed rate over surface roughness. So what is the variance between these two? So how we are going to determine if there is a significant variance or not? So by using this F value, the variance between the means of two populations, that is cutting speed and feed rate, is significantly different or not, that I can identify. By using from the F value, we are going to determine the P value. The F is the Fisher value, the P is the probability value. The probability of getting a result at least as extreme that we can observe based on the assumptions made in the null hypothesis. So the probability of getting a result as least as extreme that is observed based on the assumptions of the null hypothesis. So this F value should be as much high as possible, so that that factor will be more significant, and the P value should be as minimum as possible, because we are going to carry out the statistic, we are going to perform statistics based on 95% confidence interval. So the values that are less than 0.05 are significant model terms. So for this, the F value should be higher. P value is calculated based on the F value. So obviously the P values will be lower. So reject the null hypothesis when the P value is smaller than your alpha value. So we have to check for the both F value as well as P value, but we have to reject the null hypothesis when the P value is less than the alpha value. In the null hypothesis, we are going to assume that there is no significant variance between the independent variables. There is no significant variance between the two independent variables. But with P value less than the alpha value, Since we are going to carry out with 95% of confidence interval, the alpha value is 0.05, that is 5%. So if the p-value is less than this 0.05, a significant variance exists between the two parameters. But my null hypothesis is there is no significant variance. But if p-value is less than 0.05, there is a significant variance. So I have to reject the null hypothesis and I have to accept the alternate hypothesis. So what are the different types of ANOVAs that we normally have in statistics? One-way ANOVA, then two-way ANOVA, factorial ANOVA, then mixed design ANOVA, then M ANOVA. We call it as multivariate analysis of variance. But in this, we are generally going to have a factorial ANOVA without any interaction terms. So what are the basic steps in ANOVA? So the ANOVA is nothing but the decomposition of total variability into its component parts. So we are going to decompose the total variation. There will be a total variation that I am going to decompose into the component part, that is depending upon the input parameters that we are selecting. So the total sum of squares is equal to sum of squares of treatment plus sum of squares of error. So the sum of squares is represented by SS, capital SS, and total is equal to SSA of A. A is nothing but the input parameters. And error, there will always be an error, and that should also be included in that. So here we have some formulas for this. So N is nothing but the number of experiments, and that is associated with the degrees of freedom. The degrees of freedom for individual treatment is equal to A minus 1. The A is nothing but the number of level values for a particular treatment. For example, take a cutting speed. The cutting speed is varied by 3 levels. Level 1, level 2, level 3. So 3. So here A is equal to 3. So 3 minus 1 is the degrees of freedom for a treatment. For the mean sum of squares of error, the degrees of freedom is calculated based on the total degrees of freedom, which is nothing but the total experiments minus 1. So the total degrees of freedom is the total number of experiments minus 1 minus the individual treatment, degrees of freedom of each and every treatment. So that will come to the residual errors, degrees of freedom. So this is the formula that relates to the ANOVA table for a single factor. So here we have between treatments, within treatments, and total, and all these things. Here we have the formulas. So based upon these formulas, we can calculate. Similarly, this is the generalized format for ANOVA for 3-factor factorial design. So yesterday we have seen factorial design. So 2 power 3. So here we have taken 3 parameters A, B, and C. So 2 power 3, which is equal to 8 experiments, in which I am going to consider the interaction terms also. So AB, AC, BC, and ABC terms also. So based upon this, we are going to determine the sum of squares, degrees of freedom, as per the formulas that is given. So I will tell you how to calculate this by a model calculation at the last using an example. So don't get panic. The procedure to formulate ANOVA table. So in formulating the ANOVA table, the foremost thing that I have to do is the selection of input parameters, then making an experimental design, then I am going for the experiment, record the outputs, then analyze the outputs, and in the final we will go with the analysis of variance. The first compute the correction factor. We call it as the CF. So CF is equal to T square divided by N. No need to note all these things because we will provide the PPTs on all these things. So CF is equal to T square divided by N, where T is the grand total and N is the number of observations. The grand total of the output. For example, flank pair means if I am going to run a L9 orthogonal array means 9 values I am going to just add. So that is my T. So the T square divided by N. The number of experimental run is 9. So T square divided by N. Now the total sum of squares is computed using the formula. So sigma ya square I is equal to 1 to N minus CF. So this y is the square term of each and every output. Since we have 9 outputs, each flank pair value should be squared. And finally, I am going to sum up that and I have to minus that from the correction factor. So here you can see how to calculate the individual sum of squares. So here we are going to consider 3 factors. Factor A, that is the independent factors. Factor A, factor B and factor C. The sum of squares of factor A is determined by A1 into 3. What is A1 here? We are going to have a response table, that is nothing but the making the average. We are going to make the average that relates to the similar level values. Yesterday itself we have seen. So we are going to formulate the response table making the average that relates to each and every level values. So A1 corresponds to level value 1. The response, the average value corresponds to level 1 into 3. Because here we are going with 3 level factors. So 3, the whole square divided by NA1. The number of times the level 1 value is repeated. In a L9 orthogonal array, each level is repeated by 3 times. So NA1 will be 3, NA2 will be 3 and NA3 will be 3 minus the correction factor. The total sum of squares, first we are going to determine, then the individual sum of squares we are going to determine. And the final thing is we have to compute the total sum of squares for error term. So which is nothing but the difference between sum of squares of total minus the sum of squares of all treatments. The sum of squares of all treatments. As here we have taken 3 independent variables A, B and C. The sum of squares of all the treatments are grouped together or summed together and that is subtracted from the total sum of squares. That will give us the error sum of squares. So the error sum of squares is due to the replication of the experiment and that may be also called as experimental error or pure error. So we have to include the error term in all these models. So this ANOVA also contains an experimental error or pure error because of the replications. So this is the procedure to formulate an ANOVA table for the orthogonal arrays that we are going to use. So here I am going with 3 parameters. I am going with 3 parameters without any interaction term. Without any interaction term. So I have parameter A, parameter B, parameter C. So the degrees of freedom for each parameter is the number of level values minus 1. For example, parameter A has 2 levels. For example, if parameter A has 2 levels, then the degrees of freedom is 2 minus 1, which is equal to 1. If the parameter B has 3 levels, then degrees of freedom is 3 minus 1 is equal to 2. So obviously it is a mixed level design. So now for this example, we are considering three levels for all the parameters. Then based on the formula that we have used here, the last formula SSA is equal to A1 into 3 the whole square. By using this formula, I am going to determine the sum of squares for parameter A, parameter B and parameter C. And also by using the formula, I am going to determine the total sum of squares. By eliminating by subtracting the summation of sum of squares of all parameters from the total, I am going to determine the sum of squares of error. So from this, how to calculate the mean sum of squares? So the individual sum of squares divided by degrees of freedom of the individual terms. Mean sum of squares divided by degrees of freedom of individual terms. So mean square is equal to SSA divided by degrees of freedom of A. Similarly for parameter B, its sum of squares divided by its degrees of freedom. Similarly for error term, mean square is equal to error sum of squares divided by error degrees of freedom. Right. Now coming on to the Fisher value, F value. F value tells us the significance. So here the mean sum of square of parameter A divided by mean sum of squares of the error term. So it is the ratio of mean sum of squares of individual term divided by mean sum of squares of the error term. So similarly for all the parameters we are calculating. If I am going to calculate for interaction term, then for that also we can calculate. Now coming on to percentage contribution. The percentage contribution is the ratio of individual sum of squares divided by total sum of squares. In the case of parameter A, percentage contribution is sum of squares divided by total sum of squares. Parameter B, sum of squares of parameter B divided by total sum of squares. Similarly for error, and the percentage contribution for total should be 100% because the percentage contribution for total is total sum of squares divided by total sum of squares, so it should be 100. Why you are telling it 100 is we are giving that in percentage, so it is 100%. So now here we will have an example. This example yesterday we have seen for Taguchi's DOE. So here we are going to have three level values for three parameters. Parameter 1 is the cutting speed, then feed rate and depth of cut. So it has three parameters. So obviously I am going to choose a L9 orthogonal array. So I have formulated this. And then the output that I am going to obtain is the chip thickness ratio in the last column. So that is my output that I am going to analyze. So based on this chip thickness ratio, I am going to determine the variance that exists between cutting speed and feed rate, and between cutting speed and depth of cut, and also between feed rate and depth of cut. Here I am not going to use interaction effect, because if I use that interaction effect, obviously my degrees of freedom for error will become zero. So if the error degrees of freedom is 0, I cannot compute the ANOVA table. So in this, the interaction terms is omitted. So first I am going to formulate the level response table. This response table, how we have formulated is by taking the average. So consider this cutting speed. The level 1 value is 120, 120, 120, which is in the trial 1, trial 2, trial 3. So what I am going to do is, I am going to add the chip thickness ratio that corresponds to experiment 1, experiment 2, experiment 3. So 0.44 plus 0.49 plus 0.53 divided by 3 will produce 0.487. Similarly for level 2 and level 3. In the case of rate, consider the second level value of 0.07. So trial number 2, trial number 5 and trial number 8. So in this case, the trial number 2 value is 0.49, for 5 is 0.52 and for 8 is 0.35. Just add and divide it by 3 and we will have 0.453. So similarly, compute this response table. So the first procedure in determining in formulating the ANOVA table is calculation of correction factor, which is equal to t square divided by n. The total of all these values, is 4.030. That is, these chip thickness ratio values I am going to add 0.44 plus 0.49 plus 0.53 plus 0.47 plus 0.52 plus 0.43 plus 0.42 plus 0.35 plus 0.38, which is equal to 4.030. That I am going to square divided by 9. What is this 9? In L9, we are going to have 9 experimental trials. So I am going to use it as 9. If I am going to replicate, then I have to take it as 18, but you should also consider that 9 values also. You should also consider that 9 value also in T. So the correction factor is 1.805. Now we are going to compute the SS total. The SS total is computed by summing up the square terms of individuals and then getting subtracted it from the correction factor. Here, the chip thickness ratio, the first trial value is 0.44. Now I am going to square. So 0.44 square plus 0.49 square plus 0.53 square plus 0.47 square plus 0.52 square plus 0.43 square plus 0.42 square plus 0.35 square plus 0.38 square. That will come to 1.8341 and my correction factor is 1.805. So the difference is 0.0291. That is, the total sum of squares is 0.0291. Now I am going to calculate the sum of squares of individual terms. The SSA, A is nothing but the cutting speed. The A1 corresponds to the level 1 value of cutting speed, and the A2 corresponds to the level 2 value of cutting speed, and the A3 corresponds to the level 3 value of cutting speed. So which is equal to 1.46 square, that is A1 into 3. So 0.487 into 3, that comes to 1.46. Similarly, A2 into 3. So 0.473 into 3, 1.42. Then 0.383 into 3, 1.15. That square divided by level value comes 3 times in the 9 experiments. Level value 1 comes 3 times, level 2 comes 3 times, and level 3 comes 3 times. So we are dividing it by 3. If I am going to take two level, then I have to divide it by 2. If I am going to consider 4 levels, then I have to divide it by 4. So this is the simple calculations. So that minus 1.805, which is equal to 0.019. So that is the sum of squares for cutting speed. Similarly, we are going to calculate or compute it for the sum of squares for feed rate, the sum of squares for depth of cut, and then we are going to record it here. So here the degrees of freedom. So be attentive in this. This is very much important. So in cutting speed, I have 3 levels. So my degrees of freedom is 3 minus 1 equal to 2. For feed rate, 3 levels. So 3 minus 1 is equal to 2. And for depth of cut, the total level is 3. So 3 minus 1 is equal to 2. Coming on to the total degrees of freedom. Here we have considered L9 orthogonal array. So the total number of experiments is 9. So for the total experiment, the degrees of freedom is 9 minus 1 is equal to 8. Now computing the error degrees of freedom, which is equal to total degrees of freedom minus the degrees of freedom of cutting speed minus the degrees of freedom of feed rate minus the degrees of freedom of depth of cut. So 8 minus 2 minus 2 minus 2, that comes under 2. Now adjusted sum of squares. So at the adjusted sum of squares we have calculated here. For SSA it is 0.019. So that is more accurate, 0.0189. So this is system generated. We have formulated it by using Minitab. So that also we will see later on. So this is for 3 digits and that is for 5 digits. So it is nearby value. Similarly, I am computing it for feed rate, depth of cut, and then total. Total we have calculated as 0.029. So 0.0291. So exactly it is computed. Now mean squares. We have to calculate the mean squares. So mean squares is equal to individual sum of squares divided by individual degrees of freedom. For cutting speed, the adjusted MS is equal to adjust SS divided by degrees of freedom, that is 0.018956 divided by 2, which is equal to 0.009478. Similarly for feed rate, adjusted MS is equal to 0.000156 divided by 2, which is equal to 4078. Similar for depth of cut, 0.010422 divided by 2, which is equal to 0.005211. So similarly for error term also we are going to determine the mean square. Then comes the F value. The F value is equal to mean sum of individual divided by mean sum of error. Here the mean sum of squares for error term is 0.000011. So the F value of cutting speed is computed as 0.009478 divided by 0.000011, which is equal to 853. Similarly for feed rate, F value is equal to 0.000078 divided by 0.000011. Similarly for depth of cut. So the p values we will take from the statistical tables. We have to take it from the statistical table for an alpha value of 0.05. Since we are going to carry out the stats ANOVA based on 95% of confidence interval, the alpha value is 0.05. So the p value is computed for an alpha value of 0.05 for the F value and degrees of freedom, based on the F value and degrees of freedom. So how to calculate this percentage contribution in the last column? The percentage contribution is sum of squares of individual divided by total sum of squares. For cutting speed, the sum of squares is 0.018956 and for total is 0.029556. So the percentage of contribution for cutting speed is 0.018956 divided by 0.029556. Similarly for feed rate, individual SS 0.000156 divided by total SS 0.029556. So that is 64% and this is 5%. I have not converted into 100. So 64%, then 5%, then depth of cut contributes by 35%. And the ANOVA, the error term is 0.07. So put together it should be 100. So put together it should be 100. Or I will correct it now. So it is around 64 point. Put together it is 100. So that is the procedure to formulate the ANOVA table. So hope you've been well versed with this ANOVA table, how to formulate the null hypothesis and what are the assumptions that is to be made and the formulas that relates to the ANOVA table, how to manually work out an ANOVA table for this orthogonal array or for full factorials. And now we are going to work out this example in Minitab and we are going to compare, because the system itself will give us the table, but we should know how that values are obtained. That's why we have used this. So I am going to open the tab. So since I have formulated this, I can just cut copy. Okay, this is my inputs and this is my output. And this is my output. What is the chip thickness ratio? Now, in order to determine the ANOVA, go to Stat, ANOVA. Here we have 1 by ANOVA. So analysis of means, balanced ANOVA, then mixed effect model, then nested general ANOVA, multivariate ANOVA. Now, but here we will go with general linear model, fit general linear model. In this, the response is chip thickness ratio, and the factors are these 3 input factors. Select. So here we can see the model that we have selected, the terms in the model. The terms in this model is the cutting speed, feed rate and depth of cut, and then options, whether we have to give any weightages or thing. But here you can see the confidence interval for all intervals is 95%, and type of confidence interval is two-sided. The Bell-shaped curve, the two-sided, and sum of squares is adjusted type 3. It is the adjusted type, and no transformation is required for this. And no transformation is required for this. And graphs, click on the graphs. If I want any plots, I can give. Then I can go with 4 in 1 graph. This also is possible with this. Then okay. Here we come across this. This is the analysis of variance table. You can just copy this and I can copy and paste. So now we are going to verify our results with this. So look at this. My adjusted SS for cutting speed is 0.0189. So it is also the same. So it is 853 something. So here you can see this total is 0.0291. This is 0.0291, but it is 0.02955. So it is the 4th digit is getting changed. So SSA for A is 0.019, because 0.0189. So I am going to change it to 3 digits. So based upon this, we are going to obtain these values. So this is how we are going to do. So here, probability plot. So in the previous case, we have seen that the normal probability plot should follow a normal distribution, but here this normal distribution is not available. And also here in the second versus fits, the residual versus fits, it is more randomly developed and it is on the extreme ends, that is on the lower control limit and also on the upper control limits. The histogram is not going to follow a bell-shaped curve. Is not following a bell-shaped curve, and the observations versus residual, it is more or less very small because of this R square value. The R square value obtained is 99.92. So how we are going to obtain this R square value? How we are going to obtain this R square value? Just add the adjusted sum of squares of cutting speed, feed rate, depth of cut, and divided by total, SS. That will fetch you the R square value. So R square is equal to summation of sum of squares of all the independent variables divided by the total sum of squares. So that will give us the R square value. So in the morning we have seen the ANOVA table for response surface methodology. Once again I will go back to that. So I will take the surface roughness model. Now here I am going to compute. The percentage contribution for this. So I am going to copy this and I am going to open an Excel. So here percentage contribution. So for model, the sum of squares. So here it may be visible for this. The percentage contribution is, which is equal to this sum of squares divided by the correlation total. Likewise. So which is equal to this cutting speed divided by the correlation total is 6774655. So thus I am going to copy this and I am going to make it as a percentage. So the model, here you can see the model. So the model has a percentage of 97.19. The model has a percentage of 97.19, which is nothing but the R square value also. So the cutting speed contribution is 0.22, the feed rate contribution is 8.89, and depth of cut is 0.14. And this is for the interaction terms. Now here you will come across these three things. So this 2.81 is nothing but the summation of these two things. If I am going to sum this, then I will obtain these two things. So 2.81. So 2.81 percentage So for model it is 97.19, and for lack of for residual it is 2.81. So if I am going to sum these two, I will get 100%. So the total error in this model is 2.81, and the total percentage of contribution from this model is 97.18. So in this, the influence of this, the influence of feed rate is higher, and also the influence of this, the influence of this is little bit 4.21. And comparing to others, this has some impact because of the feed rate. The other parameters are of least significance. So for surface roughness, the effect of feed rate is higher than that of the cutting depth of cut and the cutting speed. So this is how we have to interpret and how we have to write the manuscript. So similarly, we can also determine for flank pier. So now surface roughness, you can see the R square value. The R square value is 97.19. So here also you can see the model. So that is this. Or the R square value is computed is equal to summation of all these things, because don't take it as model. These are the parameters with their interaction effects divided by the correlation total. The correlation total is the, so this is, so this is R square value. So here you have a slight deviation because of the digits. Because of the digits, we have some slight deviations. So don't interpret with that. But here you can see the R square value is 97.19. So that also we can determine. So don't worry about all these calculations. We should know, but don't worry. The software will be part, but we should know why it is coming and what is the significance of p-value. What is the purpose of degrees of freedom? Yesterday someone asked. So what is the purpose of degrees of freedom? So the degrees of freedom is used to determine the mean sum of squares, and it is also useful in formulating this ANOVA table so that the significance of selected parameters can be determined. So here we can see the variance between the three parameters selected. So cutting speed and feed rate, there is a vast variance. So whatever hypothesis we are going to have, we are going to have. So yeah, variance exists. If I am going to consider a variance exists between the control parameters, then we have to accept. Otherwise, we have to reject. Hope you all enjoyed this session. And this is a very short session because it's only a small technique. But yesterday and the morning sessions, we have talked more about this ANOVA. But the formulas that is used to determine the sum of squares, degrees of freedom, mean sum of squares, F values, and percentage of contributions is you should be aware of. That's why in the session for a short time period we have taken this as a module. So now the session ends because many of them have doubts over this. So you can ask in the chat session and I will reply to you. Thank you.